Hey everyone, so I just wanted to follow up on the exercise that we didn't quite get through in class yesterday, which was our experiment in using a permutation test to not estimate but actually directly calculate the p-value of an experiment. And so we did this based on this paper. We have this nice example from this paper by Michael Ernst, and again, the reason why we care about this is, first of all, I think hopefully it helps you give you a more intuitive sense of what the p-value is. Remember, it's our type 1 error, it's our false positive rate, but also because using the sort of ugly mathematical formula for p gives us an estimate, but it doesn't give us an exact value. And the reason why we would prefer to have an exact value is not just for precision, which is always valuable, but is also because in order to use that mathematical formula, we're actually assuming that our underlying data is normally distributed. And of course, as we know, very often that isn't the case. So the nice thing about the permutation test is that it lets us leverage the fact that we have computers to precisely calculate the value of p or alpha. And I think, as I said, also provides a sort of nicely intuitive way to understand what that false positive rate is. So I'm going to flip back to the code here. What we're doing is, so just to clarify, that what we're doing in our code is exactly what is shown in this table, which is showing all of the we're actually doing permutations, this is combinations of the treatment outcomes. This is our actual values, right? So we had a new treatment. These 4 readings are the recovery times of the patients using that new treatment. These are the 3 times of the three recovery times of the patients using the standard treatment, and this is the difference in means. And so our question is, what is the significance of this new treatment? Is this statistically significant, the difference that we're seeing? So flipping back to the code that we looked at yesterday, so we have a bunch of libraries that we're importing here. CSV, you'll recognize. NumPy, I think you'll recognize, and certainly Matplotlib. Statistics. itertools is just a nice package that lets us automatically generate those permutations, which is what we want to do. So we're kind of doing more than we have to here, but it's fine. It's a very small data set. It's not going to negatively affect performance. So again, just to walk through here, we're starting with the actual difference in recovery times that we observed between our 2 treatments. And remember that our H0 is always framed in the negative. So we're always assuming that there is no difference between the treatments. It follows from that if there's no difference in the treatments, then the recovery times are essentially all the same. That's what lets us do this permutation test. So we're basically saying, look, all the recovery times are the same. There's no difference in whether you got the new treatment or the old treatment. So we're going to just lump all of our results together into a single array, and now we're going to generate all possible permutations of that array. I'm creating a list where I'm capturing all of the differences. So I'm going to call this arithmetic differences, right? So subtraction between, I'm going to say, the means sampled data, right? So in other words, what I'm saying is every time I resample, so I'm going to go through my list of permuted, I'm going to go through my permuted list. I'm going to take four elements and then 3 elements. I'm going to calculate the mean of each. I'm going to subtract those from one another, and then I'm just going to save that into a list. I'm just going to see what that difference is. And then at the same time, just for kicks, I'm going to track how many of those differences, how many of the differences that I get with my permuted data are greater than the actual observed difference between my 2 treatments, right? So I have a real reading, and then I'm sort of doing this, I think of this as like synthetic data. So again, I like to have an iterator. It's kind of how I grew up programming. So this is a way where if I want to keep track of which element I'm at, I could actually print this out. I is just going to literally give me the position that I'm in. So the first time through it'll be 0. It's always 0 index, so it's going to be 0, 1, 2, 3, etc., all the way up to the list of the length of my list. Now I'm just saying right, choose ladder 3 elements. Add the difference, sorry. I'm actually calculating the mean in situ there, right? Right? So again, I've got to get rid of these pop-ups. I'm adding the difference between the two means to that list of potential differences, right? So if this were real data, if these were the observations that I had, this is how they might behave. And then I'm just saying if the actual, if the potential difference in between my permuted means is greater than actual increment greater than observed, right? So it starts at 0. I'm going to just add 1 to it every time I see an increase. And just because I would like to know, I want to say, okay, what's the length? How many means do I have? How many differences am I looking at, which is actually the same as the length of my permuted list? How many of the differences between those is greater than what I observed in my actual experiment? And then I'm doing a proportion. So the proportion of the cases where the mean is greater than our treatment case. Now, this is because we are looking for, what we're seeing is what we observed was a decrease in recovery time. And so anything that is greater than that, right, is going to be a non-positive impact, right, on the recovery time. Think of it, again, having to reverse things a lot here. And so that means that 1 minus that value, right, 1 minus the number of observations that are higher, that are longer, 1 minus the number of recovery times that are longer than our observed recovery time is actually going to be our p-value. And that, again, is our precise p-value. So then I'm also going to just plot a histogram of this, right? I want to see where all the values of potential means, where all of the permuted means show up. And then I'm going to plot a line where my actual observation was. So hopefully this sort of clarifies what's happening here. I'm going to go ahead and run this. Okay, and let's see what we get. Whoops, how can I show my window here? Okay, so here we go. I'm just going to pull this over here. What I see is, first of all, the values. So what have I printed out? I've printed out first the number of permutations I have. That's 5,040. This is the number of instances where the mean difference between my sort of synthetic or resampled data points was greater, right, larger or longer, the recovery time was longer than what I observed in my actual experiment. That's 4,608. All I'm doing is, this is a length because this is an array, this is an integer, which is why I don't have to do a length on it. So the number of times, so the percentage of observations in my resampled data that I made with that permuted list that is longer recovery time than the one I actually observed is 91% of the time, which of course means that the times that it is shorter than my observation is about 8.5% of the time. And if we look at the plot, we see something like this, okay? And so, again, what we're seeing here is this is actually a precise calculation of what our p-value is. So, you know, the question of, is p less than 0.05? It's not. It's less than 0.10. Now, do we care? What are we looking for? Those are all experimental design questions, right? Those are not things that we can change after the fact. But again, the key thing here is that what we're getting is a precise description of what the alpha or false positive rate is for our given experiment. Again, also doesn't address things like the power of the experiment. We would probably never do this based on 7 samples, et cetera, et cetera, et cetera. But hopefully this clarifies what the p-value is actually measuring and gives you an idea of what the mathematical formula for a p-value is trying to achieve. Also kind of cool that we can just skip that and instead calculate it precisely. So if you have any questions on this, please feel free to post them to Piazza, but just wanted to make sure that we got a chance to go through that together. Okay, see you next time.